Now we're going to look about how we take advantage of half-lives, in particular for carbon-14, to understand how we date objects through the use of radioactive dating. Let's look at how we can use carbon dating to determine the age of an object. Now, carbon dating is adequate up to about 50 or 60,000 years. Beyond that, we have to use other isotopes, but the principles are still exactly the same. So let's look at an example shown here. So if we have a living thing, a plant, a tree, a person, whatever, there is a certain ratio of carbon-12 and carbon-14. So carbon-14 is just a particular isotope of carbon that exists in nature. And there's a specific percentage of it that we know, and we can use that as our reference point. Now, what I'm showing here is not an exact representation of that percentage. I show you that it's about 60% carbon-12 and about 40% carbon-14. In reality, the amount of carbon-14 relative to the amount of carbon-12 is much smaller. I've expanded it here to make it easier to see. So what we see is when we have a living thing, we have some ratio of carbon-12 to carbon-14. And as long as that thing is alive, it will maintain that ratio. Once something is no longer living, there's no more intake of carbon, and what happens is carbon-14 begins to decay and forms nitrogen-14. So as soon as something stops living, the amount of carbon-12 is constant, okay? But the amount of carbon-14 begins to decrease. So when we look at carbon-12 or carbon-14, we see that it has a half-life of 5,730 years. So imagine that we started with 60 grams of carbon-12 and 40 grams of carbon-14. After 5,730 years have passed, we will still have our 60 grams of carbon-12, but now we will only have 20 grams of carbon-14, and the remaining 20 has been converted to nitrogen-14. After two half-lives, or 11,460 years, we still have our 60 grams of carbon-12, we have 10 grams of carbon-14 because that's half of 20, and now we have 30 grams of the nitrogen-14, the 20 plus 10 more. And this process continues. And notice as we do this, the carbon-12, carbon-14 ratio continues to change, and it continues to decrease the amount of carbon-14. And so by determining this ratio and seeing how it's changing over time, we can determine the age of an object. So for example, if we knew that a sample had a ratio that was 1/4 of the value it was originally when the item was living, so if it's 1/4, that means we've gone from 1 to 1/2 to 1/4, then we know that we've had two half-lives. Here's half-life number 1, and here's half-life number 2. Remember, the 1 is at time 0. So that's when the object was still living. So we have two half-lives, and so that tells us that we can determine that the age of this object is about 11,460 years. Now, it's not exact, but it does give us an approximate time. Now sometimes things are dated such as parchment or things that were made, paper that was made from trees, and we can do this because there's not a huge gap of when the tree was cut down until when the parchment was made. So we can still use this to approximate the age. So if we said, well, it's two half-lives, then that could be anywhere between 11 and 12,000 years, for example. So let's look at another example. The carbon-12, carbon-14 ratio is 1/8 of its original value. What is the approximate age of the object? Think about how many half-lives it would take to get to 1/8, and then figure out how old that object would be. Remember that the half-life of carbon-14 equals 5,730 years. Remember that at time 0, we have the whole amount. We have the 1, the full amount of substance, whatever that amount is. In this case, we're dealing with our ratio. The original ratio we represent by 1. Then we go to 1/2, then to 1/4, then to 1/8. And what we see is that this is 3 half-lives. A common mistake is to count this as 1 here, but we remember that the half-life is the time between going from the original amount to half of the original amount. So 1 half-life, 2 half-lives, 3 half-lives. So if we have something that's 3 half-lives long, we can say that the age of that object is 5,730 times 3, which equals 17,190 years.